It can be very confusing to think about the difference between percent saturation of hemoglobin with oxygen versus the content of oxygen in the blood. So let me walk you through that. The x-axis is the same partial pressure of oxygen per millimeter of mercury that we've been talking about all along, but I'm going to make the y-axis now be amount rather than percent saturation, amount of oxygen per liter. Remember that at approximately room temperature, body temperature, somewhere around 5 mils of oxygen can be dissolved in a liter of water. At human body temperature, somewhere around 6 mils. I'm just going to say 5 milliliters here. And so this is the amount of oxygen you would expect dissolved in water at a partial pressure of 160 millimeters of mercury. You would expect the line to look like that. As the partial pressure of oxygen increases, so does the amount of oxygen that can be held in this case, blood. Now that's a very low amount of oxygen, and we can increase that by using hemoglobin. So let's imagine a very small amount of hemoglobin is present. Now on top of the oxygen dissolved in blood, some can be held in the hemoglobin. And we might have a curve that looks like that. That's a tiny amount. If we increase, we get a little bit more. And as we get a little bit higher, we start to see the typical sigmoidal S-shaped curve. I'm drawing this with more and more hemoglobin. In this case, we're saturating somewhere around 80. This is increasing amounts of hemoglobin. Notice that the curve does have the same shape all the time. At least I'm trying to make it have the same shape. In each case, I'm trying to get it to the point where it's nearly 100% saturated at 80 millimeters of mercury partial pressure of oxygen. In terms of percent saturation, somewhere around 80 to 100, we're 100% saturated. Somewhere in this vicinity, we're at 100% saturated. All of these different curves have a different amount of total oxygen, but in each case, they're 100% saturated. For example, a human that was at sea level would have a certain amount of hemoglobin in the blood. Moving to high elevation would stimulate the production of more red blood cells and more hemoglobin. The hemoglobin molecules are exactly the same, so they'll have the same affinity curve with 100% saturation somewhere in the range of 80 to 100 millimeters of mercury. But that person living at high elevation will have more hemoglobin and therefore would have a higher total, still 100% saturation. Animals that move from lower to higher elevation have the same curve, but as they move to that higher elevation, they produce more hemoglobin and have more total content of oxygen per milliliter of blood. We have three concepts. That are all important for understanding oxygen transport. One is how efficiently the organism picks up oxygen, with countercurrent being highly efficient, a tidal lung and external gills being very inefficient. The second is how tightly the hemoglobin holds on to oxygen, with very high affinities, picking up oxygen easily and releasing it only in areas of very low partial pressures of oxygen, versus curves in which it's not as easy to pick up oxygen, but it's easily released in areas of low partial pressure. Third, the amount of oxygen per liter, in which you might have identical hemoglobin, so these could be exactly the same hemoglobin, with the same curve. Notice that they're nearly 100% saturated here at perhaps 80 millimeters of mercury. Both are 100% saturated. Both have lost about half of their hemoglobin at something like 40. So they're identical curves. They're 100% saturated at the same point, but with more hemoglobin, with twice as much hemoglobin, this individual has twice the oxygen in milliliters of oxygen per liter. It's important, as you're thinking about these, that you realize that these concepts are interrelated but not the same thing. You need to think about mechanism of uptake. How easily do you pick up that oxygen? In other words, how much work do you have to do and how quickly, and can you load your blood with oxygen even at low partial pressures of oxygen? That works best with countercurrent exchange and is inefficient with tidal lungs and external gills. The affinity of hemoglobin for oxygen, which is related to whether or not there's selection pressure to pick up oxygen and maximally load hemoglobin at a particular partial pressure, or to easily release oxygen. So this conserves oxygen in areas of low partial pressure of oxygen. This easily releases oxygen. Finally, how much hemoglobin do you need to carry per milliliter of blood? The more hemoglobin per milliliter of blood, the more oxygen will be carried. The affinity curves themselves may be the same, 100% saturated at the same point, but the amount carried will be different.